All right, here we are, part 3 of 3. Get our second tree diagram example done. All right, so this one was an interview with Tom Hanks. 80% of the people of the population are caring and truth-telling, and the other 20% are crooks and liars, right? So it's a quote from Tom Hanks. So a new lie detector suit, right, correctly identified truthful people 88.9% of the time, liars 75.6% of the time. And it says a positive test in which a person is identified a liar. A negative test means they are identified as truthful, right? Regardless of whatever they actually are. So when I set this up, I'm going to have the person be first, right? So we either have they are truthful, right, or they are a liar. Truthful 80%, liar 20%. And then if they are truthful, right, the test should come out negative if they are truthful, if they actually are truthful. So that should be 0.889. And then positive test 111. So even if they are truthful, there's about an 11% chance that they turn out to be, or come out from the test as a liar. Okay. So then we have the same thing with a liar. So we have a positive test and negative test. So if they are a liar and the test comes out negative, it says that they are not a liar, right? That they're truthful, right? So we're actually saying the liar, the 75.6, is a liar, and it comes back as identified as a liar, right? So correctly identified. So positive test, if you are a liar, that's a good thing, right? Which means the negative, right? 1 minus 0.756 is 0.244. All right, and there's our tree diagram. All right, this gets into the idea of false positives, false negatives. Right, if you don't know what a false positive or false negative is, a false positive would be, you take a test and it comes back positive. Like say you take a test for a certain disease or something like that. In antibodies or something, it comes back saying you have it. The test does, when in reality you really don't. False negative is the opposite. Test will come back negative that you don't have it, and it turns out that you actually really do. So, assuming that Tom Hanks and the company is they are telling the truth, right? So we have to assume that. Randomly select a person, test positive for being a liar. Find the probability that this person is a liar. So that would mean that knowing they tested as the liar, so first we got to find the probability, or we want a probability of a liar given that it is a positive test, right? Because if it says the test positive for being a liar, so that's the given, and in fact that they are a liar as well. So the fact that you are so following our little formula again, you don't have to use the formulas in this. You really don't need to throughout the whole chapter, but if it helps, that's fine. So a liar and testing positive, so this would be 0.20 times 0.756 all over, right? All of the positive tests, which would be 0.8 times 0.111 plus 0.2 times 0.756. And if we do that, right, we've got 0.2 times 0.756, right? So that would be 0.1512 over 0.8 times 0.111, 0.2 times 0.756 over 0.24. And we take those numbers, go to the other side, divided by 0.24, and you end up with 63% chance that if they did test positive, or knowing they tested positive for being a liar, they are in fact a liar. All right, so there's example number 2. All right, and just like the last thing we wanted to cover or talk about is if we had the mutually exclusive, right? So we had kind of like the special case for the addition rule. We also have a special case for the multiplication rule, right? So this would be if you have the multiplication rule, and this would be if you have independent events. Okay, so basically, if you think of the multiplication rule, right, from above, right here, that's the general one. And we said that if they are independent, we know that this, the probability of B given A, is the same as the probability of B. So our multiplication rule for independent events, we can write as A and B is equal to the probability of A times the probability of B. Okay, and that one can be extended to multiple events. It just doesn't have to be two. Like the addition rule, you can have 3, 4, 5 different events if you want, or even more. Uh, so, kind of similar, right? Because you can just take the individual probabilities and multiply them together rather than add them together with the addition rule, right? So the example I have for that one, right? We have here's a test with a non-invasive test during the first trimester. And it gives us a 5% of normal pregnancies will receive a positive result. All right, so what's the probability that at least one of them, right, if you tested 100 women, probability at least one of them receives a positive result? All right, so we have to assume the individuals are independent, so that's good. So we can just multiply the values together. We don't have to worry about any givens or conditionals. So we want, and I think this, instead of, when it says at least one woman is positive, that means it could be one woman positive, two women positive, three women positive, all the way up to 100 women positive. That's a lot to do. So instead, what I might do is the only way this doesn't happen is if I find out the probability that there's no positives, right? Because if there's no positives, that's the complement of at least one, right? So, and I want to kind of mention this, that when you do at least one, say you did one woman receives a positive result and only one, you can't say, oh, it's positive on the first, and then you do say 0.05 times 0.95 to the 99th. That's only that one way. You can also be the second woman, the third woman, the fourth woman, the fifth woman. So there's 100 ways of that, and then you get into, if there was two, it could be the first and the second, first and the third. There's a ton of ways to do that. We'll actually talk about that with combinations. But the only way it doesn't happen, or this isn't fulfilled, is if you have no positives, no positive tests. So that means we have all 100 negatives. So all 100 negatives, which means we're going to take 0.95, right? Because that would be a negative result, since 0.05 is a positive, right? Times 0.95 times 0.95 times 0.95. Or in other words, it'll be 0.95 to the 100th. Okay, and that's going to come out to 0.95 to the 100th. You end up with 0.0059, right? So if we want at least one positive, at least one, that would just be 1 minus the complement, which is none. So 1 minus 0.0059, and that would leave us with 99.41. All right, so about a 99.41% chance that if you tested 100 women, you have at least one positive result. All right, so there you go. That's all of chapter 5.2, or I'm sorry, 5.3, part 3. Let's get to it.